Um, Maybe I'll start. Hi, welcome to this distinguished colloquium. I'm Sanjeev Arora from the Computer Science Department. And it's my great pleasure and honor to welcome Jon Kleinberg on his electronic visits to our department today. Jon is one of the giants of computer science, and he's been instrumental in taking it into exciting new directions for the last 2 decades. He got his PhD in algorithm design at MIT, and then immediately started applying those insights into new areas of computer science. In the late 1990s, as the internet was taking off, he invented a landmark algorithm for web search, namely the HITS algorithm, which really marked the start of the internet era and influenced search engines, which really tied the internet together. As the internet took off, suddenly computer science became interested in network science, and then Jon made some seminal contributions to that, and especially in connecting it to algorithms. His work has been awarded many prizes, including the Neville Prize, the ACM Prize in Computing, the MacArthur Fellowship, and many, many other fellowships. So without further ado, here's Jon, and he's, as usual, thinking about new things, and he's teaching a very interesting new course on this topic. And his topic today is monoculture and simplicity in an ecosystem of algorithmic decision making. And just a word about how we'll run the seminar. I will be monitoring the Q&A, and you're welcome to enter your questions, and I'll periodically lob them over to Jon. We will stop around 5:20 or 25, and we'll have more questions after that. And if you have questions beyond that, we can also promote people, Emily and I, the hosts, to the panel, so you can chat with Jon later on. So without further ado, welcome, Jon, and really looking forward to your talk.
Well, thanks very much. Let me share my screen here. All right, so are you able to see that?
Yes.
Okay, that's great. Okay, yeah, well, thanks very much for having me here today. It's a pleasure to get to take part in this, even if only virtually, and to have had a chance to connect with a number of people at Princeton earlier in the day and to have a lot of interesting conversations. So I want to talk about some work that I've been doing over the past few years on algorithmic decision making. This will be joint work with people from a number of different areas, with my student in computer science, Manish Raghavan, and then with faculty from 3 different disciplines: Jens Ludwig in behavioral, in public policy, Senthil Mullainathan, a behavioral economist, and Cass Sunstein, a professor of law. And in a way, it's inspired by some of the same issues that were motivating a talk that I gave at Princeton in spring of 2019 in a very different time. The work here is really exploring a set of different directions from that one, but with some of the same underlying high-level motivations. So, I mean, obviously, this is a challenging time where the challenges are being unequally felt by different of us, and I think in a situation like that, all of us are naturally inclined to think about how skills that we have at our disposal, or intellectual tools we have at our disposal, can be brought to bear to help in different situations. And obviously, some of the thinking here comes out of that also. And in order to think about that, more directly, it's useful to go back to how normative issues began to make their way into our thinking about computing systems, and how it became such a big component of research in computing at the moment. In a way, it's useful to start this picture back, say, in the mid-1990s, as an idea that was really mainstream in fields like human-computer interaction at the time began to pervade the field of computing more generally. And that was the idea that the computer systems that we're building really shouldn't just be thought of as being organized along a technical axis, but that there really was this second axis, right, a social and economic axis along which to think about these computing systems as well, that in some sense we were truly building socio-technical systems, right? Things like the World Wide Web, things like large social media systems, content sharing systems, and e-commerce systems, right? Now, as we did this, and as a lot of ideas developed around this, we of course began seeing that, as we moved around in this rich two-dimensional space, the systems began to rebound against our efforts at design in ways that perhaps should have been expected, but were often surprising, right? So they often were awash in misinformation. They gave rise to conflict and polarization. They made decisions about groups that began to exhibit evidence of systematic bias. It was almost as though there was kind of a third dimension going on that was impinging on our efforts at design that was gradually coming into focus. And I think, over the last 10 years or so in the field of computing, there's really been increasing interest in this what you might call third axis in this design space, in a sense, a normative axis, right? Where we ask about the outcomes that we want from our computing systems, the societal outcomes that we want from our computing systems. And to really appreciate that this is a distinct question from designing in our earlier two-dimensional socio-technical space, right? The fact that an actor has a deep understanding of both the technical and the social dynamics at play in what they're building does not mean that they will necessarily use it for desirable outcomes. That in the end is a separate question, and the evaluation of those outcomes is a separate question. And so that in some sense is going to provide some of the framing for my talk. One reason why these issues became particularly salient in the design of computing platforms over the past 10 years is a trend toward taking technologies like machine learning, where we had sharpened our techniques often in the online domain, and beginning to move those into what you might call high stakes decision settings in the offline domain, right? So in a sense, one way to think about how this works, and this is sort of a progression which I've found it useful to begin with in a number of talks on this topic, was to think about the kinds of prediction methodology that we had refined in settings like ranking and recommendation for online content, right? As in this example of a Netflix recommendation help page, where we take a user, we map them to a set of features, and then we make a prediction, like how many stars do we predict they will assign to this movie? And we begin asking ourselves, the extent to which we can think about how these might operate in what we think of as offline domains, right? In areas like hiring, for example, where there's been a growing interest and an enormous number of challenges, and thinking about how might we take some sort of a machine learning prediction methodology and apply it to problems like evaluating candidates for jobs, right? On the one hand, there's something that's there's an appealing syntactic analogy to the recommendation setting. After all, in the online domain, we have individuals, we map them to features, and we make a prediction about them. In the case of something like a job application, we have someone with their complex past work experience that gets reduced to a resume, and then it gets passed to some decision-making body, a human hiring committee, or perhaps a human hiring committee supplemented by quantitative tools, and they make some sort of a decision, right? And in some sense, the challenge in formalizing what decision they're making is at the heart of someone I'll be talking about, right? And similar things happen, right? The college application process, very similar. We take somebody's grade 9 through 12 experience, and we reduce it to a tabular feature type representation in the form of an application. But again, it gets passed to some human or quantitatively assisted human decision-making process with, again, a slightly unclear objective function. So all of this says that in many domains that we think of as residing in the offline world, there are places where we engage in what you could call screening decisions, evaluating applicants for jobs, evaluating applicants to college or graduate school, and many others, right? The act of making decisions about credit or loans is often cast as a prediction problem about successful repayment of a loan. In the criminal justice system, right, we run into these challenges around formulating decisions, for example, at a pretrial detention hearing where the law calls for the judge to make a prediction. And so because people are being asked to make predictions in all of these domains, and because they have this common template, it becomes natural for people to ask how we might try to deploy algorithms in these settings. And this is, of course, where a number of immense challenges begin to arise, right? We have seen over the past few years, and I've talked about in work that I've done, and obviously work that's been happening across the field, the danger that bias that exists in the world may make its way into bias in the decisions which our algorithms trained on data from past decisions might make. But there are other fundamental things going on here, right? And one of them is really that the idea of starting to use algorithms in domains like this, or starting to use quantitative tools into domains like this, really doesn't just represent a change at the level of scale or accuracy or efficiency. It's actually, in a sense, really a qualitative change from human decision making, right? To formulate one of these problems as an algorithmic problem is really to require us to write down a set of explicit features, right? An explicit objective function, right? If we actually want to follow this pipeline of taking an individual, mapping them to some feature representation that we could feed into an algorithm, and then actually making a prediction, it implies that we have some formalism which is going to produce that set of features, and that we have some formal notion of what is the objective function that we're optimizing. And that in the end, what comes out is a classification rule that is replicable, right? That we can, it's in the end, some short piece of code, the classifier, that we can copy, that we can put in new situations, and that we can repeatedly probe with questions. And arguably, and this was in a sense sort of some of the starting point for the work that Senthil, Jens, Cass, and I have been doing in this space, this is really very different from how humans go about making decisions, right? So I would estimate that most of us on this Zoom call have at some point been involved in settings where we've had to make judgments about other people, select other people from out of some pool of applicants for some purpose. And if you were to, and some of us in fact have a lot of practice doing this, and despite all of this practice, if you were to ask yourself, what was the precise objective function that I was optimizing in that situation, it would be very hard to actually write that down. You can write down the criteria that you were trying to adhere to, but those criteria were necessarily imprecise, and it isn't even 100% clear that you were sticking to those criteria. And this is not so much a failing on the part of any one individual, it's just this is not how humans make decisions. And there's a large amount of evidence for this, right? That even when we attempt to give the criteria for our decisions, it's not clear that we're actually able to be accurate about that. Just to make that particularly concrete, I'll mention some experiments in the behavioral sciences which have made this point. This idea that human beings don't necessarily have access to the true reasons for their decisions, and some very creative work beginning with research of Nisbet and Wilson and others in the 1970s and even earlier drew out this point, right, and tried to sort of grapple with the question of, how could we attempt to demonstrate that people are making decisions for reasons that they're not aware of, right? And so an experimental methodology that emerged here was to actually create situations where you would ask people to make decisions. You would split people into two groups. In group A, there'd be some environment which they're making decisions. Then in group B, you would subtly change some aspect of the environment. Decisions would change, but when you would ask people to explain their reasoning, the people in group B made no reference to what had changed in the environment. So I can give you one of many examples from the Nisbet-Wilson line of work. You would bring people into the lab and you would give them a word memorization task. Just ask people to memorize a series of words. And then you would ask them a non sequitur question, like name a brand of laundry detergent, as in one of their examples. Now, in group B, you would bring people into the lab. You'd give them the same word memorization task, but the words you would ask them to memorize were words like ocean, beach, moon, waves, water, and so forth. And then at the end, you'd ask them to name a brand of laundry detergent. And many more people in group B would name the brand Tide. Why is this? It's because of a phenomenon that we all are familiar with, namely priming. If I tell you to think of a bunch of words in the vicinity of some other word, then when I ask you to mention other words, you're more likely to bring that one up through the process of free association in some sort of a semantic word association network, okay? Now, that was well understood territory in a sense. What they did in these experiments was they took one extra step. They asked people, why did you pick the answer that you did? Why did you pick this particular laundry detergent? And in both groups, people who said Tide, explained that this is because it's the brand that we used at home. It's the brand I used when I was growing up. I remember the logo from the box. But people in group B did not say it's because you primed me with this word recall task. And yet we know, because many more people in group B actually said Tide, that in some aggregate sense, many people, as far as we can tell, were actually primed, right? And so people were providing explanations, even if those explanations were potentially different from what was actually influencing their decisions. And there are many, many experiments in this vein, right? In another one, you ask people to select clothing from a rack. If you orient the rack so that it's aimed at you from the left or the right, you can actually induce a strong bias to sort of take something from one end or the other. And yet when you ask people why they chose the article of clothing, it would be about things like color and style and so forth, and not about the fact that the orientation had actually, sort of greatly favored a particular choice, okay? So it creates an interesting way of thinking about, something that we often, consider when we think about machine learning algorithms, artificial intelligence algorithms, this notion of explainability, right? The complexity of black box machine learning, the lack of interpretability of black box machine learning, potentially on even very important tasks. And all of that is certainly a correct thing to be worrying about. But we should remember that humans in their own way are also uninterpretable. We are often, in fact, uninterpretable even to ourselves. We can't always know the reasons that we make our own decisions. And the fact that that we have an interface in the world that, provides explanations, that people are happy to give explanations for what they're doing, may obscure the fact that it's hard to tell the reasons for this. So these are sort of, in a way, two major changes which are happening via algorithms, and which I wanted to use as sort of a starting point for delving into some models that we might use to sort of think about what kind of changes might result from this. Right. So one is this idea that well-regulated algorithms, those for which we can actually look at the training procedure and the classifier, can be analyzed in ways that are essentially impossible for human decision making. And then this potentially provides us with avenues that we never had before, for example, for looking for evidence of discrimination, right? So in the case of a classification algorithm that's trying to engage in some kind of a screening problem for any of the examples that I mentioned before, this is not a statement that we can somehow expect to read the code and understand it, right? There are all sorts of reasons, ranging from the mathematical to the cognitive, that's very difficult. But we can do a number of things that, as I've argued, we can't really do with humans, right? We can examine the features, we can examine the labels, the loss function. We can probe the classifier with synthetic instances, right? If we want to know, would you still have made an offer to this applicant if they had graduated from school X instead of school Y? I can take that feature representation, I can change that one value from X to Y, or from Y to X, and I can feed it into the classifier, right? It's very hard to ask humans counterfactuals and have confidence in the answers that they're giving, right? I can build my own screening rule and see if I get similar answers, right? All of these are things that become possible when algorithms are involved in the decision making, right? We can really think in terms of features and objective functions in ways we can't with humans. The second point is this point about replicability, right? In the end, the classifier is a piece of code, and it can be therefore replicated. And so there's actually we get into a situation where it's possible for many, many different distinct decision makers to actually all use essentially the same structured procedure without really any local variation. Okay. And so as people, now at the moment, obviously the ecosystem which exists is, right, humans assisted by quantitative tools making decisions. But as we look ahead to domains in which there's increasing push toward automation, it becomes natural to ask, if we follow that trajectory forward and we think about settings in which increasingly decisions are being automated, what are some things that may begin to happen that look very different from what we're familiar with from human decision making? And one concern that has come up is the concern about monoculture, right? The fact that if everybody is running the same algorithm, then there's a kind of single monolithic decision being replicated, rather than the kind of heterogeneous, idiosyncratic local decisions that we see when humans make decisions in lots of different locations. So let's talk about where this might come up in the online domain. So first, monoculture, the term originates in agriculture, where the concern is, right, so monoculture, that if you plant a single crop, then you're gambling, because if a single pathogen comes along that's very effective, it may actually just eradicate your entire planting for that season, right? Whereas if you plant a heteroculture, where you have many different species, it's going to be very hard for a single pathogen to wipe out more than a fraction of the crops that you planted. People began to carry this analogy over into algorithmic domains in a few settings. So perhaps the first to get attention was in the area of malware threats to computer systems, right? And the analogy was quite direct. If we have a world in which everybody's operating system is essentially identical, then a security flaw in that operating system is amenable to attack by a single piece of malware, which might spread through the entire world. Whereas a world of heteroculture, where we run different operating systems, it's harder for a single piece of malware to spread through the entire system, right? And this has, in fact, led to arguments for, deliberately increasing the diversity of the kind of systems that we deploy to create this kind of protection. In an area closer to what I've been talking about here so far, the idea of screening methods, there was an interesting paper in 2014 by Citron and Pasquale, who again made this analogy to agricultural risk, where they argued that as people converge on a single algorithm, right, a single methodology for making screening decisions, in their example in credit assessment, one of the domains from my list earlier, then when conditions suddenly change, right, if a financial crisis suddenly strikes and the underlying conditions on which we should be making predictions have changed, then suddenly you might have massive correlated failures in ways that, again, if you had idiosyncratic local variation in your prediction rules, you might not have. And finally, the concern gets raised that, if you're someone who's sending out applications for jobs or for credit, and there's a single algorithm making the same screening decision at all the different places that you apply, there's sort of no chance for you to seek recourse if the algorithm happens not to like you. There's no chance to get a second opinion. Okay, so there's a story that emerges here, right? A kind of trade-off between deploying prediction rules that have high accuracy and that therefore might be more accurate or more efficient on average under normal conditions, versus the risk that we have worse outcomes for specific individuals and susceptibility to catastrophic failure in extreme conditions, right? In a way, these 2 points in the second bullet are related points, because, right, a global catastrophic failure is one that sweeps through, all of the entities in the system because conditions change. But even if you're somebody who the algorithm doesn't like and everybody is running the same algorithm, then that in a sense is a correlated catastrophic failure for you, okay? So there was the sense that there was kind of a trade-off going on here. So in some recent work that Manish, Raghavan, and I have been doing, we tried to ask the question, is this really the right picture, right? Is this the trade-off that's going on? Is this some way to make this trade-off precise? And as we worked on thinking about ways of making the trade-off precise, we discovered the picture is actually more complicated than this, even in very, very simple models. So if I go and try to build a model of a system where decision makers can choose between individual variation or a monolithic shared algorithm, and I try to think about what this trade-off would look like, we discover that something else is going on. That, in fact, under simple assumptions, it's actually possible, right, that you may get this trade-off, but you also may get a situation where monoculture, in fact, leads to worse average outcomes, even under normal conditions. Obviously, all of these have to be made precise, what's worse and what's normal. But even with an algorithm whose decisions are individually more accurate, okay? So what I would like to sort of talk about in the next few slides was our attempt to create a model of decision makers who can choose between monoculture or heteroculture, and how under some very simple assumptions, you have an algorithm which, if you were the only decision maker in the world, would unambiguously be the right choice to use. And yet when everyone uses it, even in steady state, even with no shocks to the system, it's causing everybody's outcomes to be worse. In a way, it's a sort of brace paradox, to take a term from traffic routing, where in the classical brace paradox for road traffic, people found the surprising discovery that sometimes when you add a road to a road system, congestion gets worse for everybody, right? You've upgraded the resources and you've actually made the outcome worse once everybody reacts to the new system. And that's essentially what our model ended up, to our surprise, producing here, a kind of brace paradox for decision-making algorithms. So how does that work? Well, to see how it works, we need to create a model. So let me sort of walk you down the road that we followed in constructing this model, and then we'll see how the brace paradox comes into play and how monoculture manifests itself. Okay, so here's the basic setup, and I'll make everything as simple as possible so that we can try to follow things in real time here in the talk. Let's imagine a world, and it's a metaphorical world in which firms are using some sort of an algorithm to rank candidates, and each candidate has some sort of numerical value that if you hire this candidate, this is the number that you'll get as a payoff. And so each firm would like to hire the candidate that has the highest number, and failing that, the candidate with the second highest number. And the numbers are the same for both firms. So these firms are in pure competition. There is unambiguously a candidate with the highest number who they would like. Failing that, there's a candidate with the second highest number who they would like instead. Now, the firms don't have exact access to these numbers. They instead are going to use noisy estimates of these values, producing a noisy ranking of candidates. And they have two choices for how they're going to do this ranking. One, they could use their own independent private ranking. Okay, so they can use their local human expertise with its own sort of idiosyncrasies to estimate each candidate's ranking, each candidate's value, and thereby produce a ranking. Or there's an algorithm that they can buy and that they can use to rank the candidates. And it's the same algorithm for everybody. So if you would like a copy of this algorithm and you pay for it, you don't use your own internal ranking, your own private ranking, you use the algorithmic ranking. And the advantage of the algorithmic ranking is it has less noise. And again, I'll have to formalize what noise means here. That'll be the next slide. But in some very concrete sense, it's a more accurate ranking. Okay. And firms compete by hiring in a random sequence. So a coin gets flipped. One of firm 2 moves first. They use one of these rankings. They pick the person at the top. They make them an offer. Again, for simplicity, we'll assume that offer is accepted. That candidate leaves the market. The next firm comes along and they move and they go to their ranking and they take the top person, who might now be unavailable because they've been hired. And if so, they move on to the second person, but they take the top person who's available according to their ranking. Okay, and that's the basic template for this game that's going to be played between two firms. Now, there are a couple of things we need to define here. I think the notion of ranking, that's just an ordering of the candidates. We do need to define noise. So the results I'll talk about actually work in a number of different models of noise, and it's sort of in part a question of taste in these modeling questions, how we'd like to represent this. One that I'll be talking about here is the so-called Mallows model, which is a standard model in the statistics of permutations, which says there's some true ranking, let's call it pi star. And there's also an underlying distance on pairs of rankings. So if I have two rankings like this, the transposition of distance between them is simply the number of pairs that are out of order. And the Mallows model is simply the distribution on all permutations that says that for any ranking sigma, the probability that I see sigma is proportional to some parameter phi to the minus distance from the truth. Okay, so on the true ranking, the distance is 0, and so it's proportional to 1 with some normalizing constant. Things that are 1 transposition away are phi to the -1, and so forth. Okay, so you could sort of think of phi as an accuracy parameter, because as phi increases, the probability falls away more sharply with increasing transposition distance, and more of the probability mass ends up on the truth. So larger phi, less noise in the system, more accurate rankings. Right, so you would aspire to things that have larger values of phi. And in our simple model, we could think of the algorithmic ranking that you might purchase, or your own internal ranking, as a, for simplicity, coming from this Mallows model with different parameters phi. But in fact, I won't get into all of the details around this, but the results we have actually generalized to sort of a much broader notion of just a noisy family of permutations that are controlled by some one-dimensional parameter where the probability mass kind of smoothly varies as I raise the parameter, getting more and more peaked on the truth. That general model also includes other formalisms like the so-called random utility model, where the candidates have true values, x1 to x2 up to xn, and each xi is then perturbed by adding random noise. Right? By adding random noise, the values shift, and the actual rank ordering of those n numbers actually also shifts, creating a new permutation. That produces a distribution over permutations. And you can think of essentially the variance of this noise as serving as sort of a version of the accuracy parameter. Right? The less variance, the more accurate. And if the variance drops to 0, the accuracy goes to infinity, and I always have the correct answer. Okay. And so the results we have will hold for a number of versions of the random utility model also. Okay, good. So that's the setup, and I think this just summarizes, right? What we have actually here is a two-player game, right? So the players have there are strategies and then there are payoffs, right? The strategy is that each firm can choose one of two rankings. An algorithmic ranking that's shared by both of them with some accuracy parameter phi sub a, or their own private ranking, which is independent between the two of them with some accuracy parameter phi sub p less than phi sub a. Okay. All right. And the game is we choose this. Then again, the firms move in a random order. The first one to move gets to take their top choice. And the second one to move takes their top choice if they're still available, and otherwise their second choice. Right? Their payoff is the quality of the candidate they get, because remember, there's a number attached to each candidate. And the social welfare, the kind of good for society, is the sum of the qualities of the two candidates chosen, right? Because in the end, we would like the sort of candidates who have the higher numbers to be the ones who are hired. So it's simply the sum of the qualities or the sum of the two payoffs. Okay, so that's the setup. And now, where does the brace paradox come in? So we began looking at this model, and this model is, despite its simplicity, a bit complicated to analyze. And as we discovered, has relatively complicated behavior, despite not really having very many moving parts at all. But in particular, the result we found was that for every value of the private accuracy, phi sub p, there exists an algorithmic accuracy, phi sub a, slightly higher, so that in this game, there's a unique equilibrium. And it's an equilibrium in dominant strategies, which effectively just means no matter what the other player is doing, you would like to play the strategy, in which both firms use the algorithm. But social welfare would be higher if both firms use their private rankings. Okay, so let's think about what this means, right? In the world before this algorithm was ever created, firms only had the option of using their private rankings. And so they, presumably in our metaphorical world here, would use them, and they would get some outcome for society. But then someone introduces this algorithm. And it makes sense they would introduce this algorithm because in isolation, it is literally more accurate. If the only firm in existence were firm one and it were faced with the choice of the algorithm or the prior ranking, it should use the algorithm. It would get a higher payoff from that. Despite that, once it's available to both of them, then monoculture kicks in. They both choose it. And in fact, now the outcome for the world is actually slightly worse. I have a couple slides in which I'll actually show something about how we prove this result. This will just be a couple slides at a very high level, just give some sense of like, how is it making things worse? But actually, I'll stop here first if anyone has any questions, either clarifying questions about this or any sort of high level questions about the goals of trying to formulate a result like this.
I don't see any questions. I hope the question feature is on, Emily, if you could check. Well, as usual, you're very clear, so maybe there are no questions.
Well, but as people think of questions, definitely feel free to interrupt me. All right, and yeah.
Okay, the feature is on.
The feature's on. So, okay, so how is it that introducing an algorithm made things worse, right? I mean, these things, like, it should be the case that this is not intuitive. It was certainly not intuitive to us because there's nothing about the setup that tells us this is okay. So here's a sort of just two slides on sort of what's going on. The first important idea is to think about analyzing what happens if things go in a fixed order. Suppose the world were not random ordering. Suppose that we know that firm 1 goes first and firm 2 goes second. Okay, and also suppose the two things are equally accurate. The algorithm and the private ranking are just the same accuracy. Suppose also that firm 1 uses the algorithm, and now you're firm 2. So you're faced with this choice: should I use the algorithm or should I use my private ranking? Now, in a world where firm 1 didn't exist, it really wouldn't matter. They have the same accuracy. It would be indistinguishable to you. They're producing the same distribution over rankings, in fact. But firm 1 does exist, and firm 1 has already chosen the top candidate from the algorithmic ranking. So now it actually might matter what you do, right? And what you can show is that actually in the situation, if you know you're moving second, you would actually get strictly higher payoff if you use the private ranking. Okay, a question: is the noise model equivalent to if each candidate has n-dimensional value? That would actually be a somewhat different, yeah. So firms with different objective functions would actually be an interesting extension that we have thought about in other contexts. But here, in a way to make the brace paradox as stark as possible, we're really saying there's a single dimensional agreement on what the quality is. So in a sense, think of it as maybe there's n underlying dimensions, but then we both use the same inner product with an objective function, and now we have the same value for each candidate. And in a sense, I think the argument is going to be the brace paradox shows up even here when there's a sense no divergence between the firms. But it's a very interesting question that we've begun thinking about with other objective functions. So, okay, so fixed order, and the argument is you should actually use the private ranking in this case. And the argument is roughly the following: that the algorithm ranks the candidates as A1 to AN. Your private ranking, your firm 2 deciding what to do, ranks them as P1 to PN. Remember, here in this example, these are the same candidates being ranked. They're just different orders. And there are two cases, really. Suppose the algorithmic ranking and your ranking agree on the first position. Okay, so these are the same thing. Then when firm 1 hires the top candidate from here, your first choice is also gone. And so basically, if you use the algorithm, you get A2, and if you use your own thing, you get P2, and these have the same distribution. So it doesn't matter what you do. But if they disagree on the first position, right? If A1, according to the algorithm, is P3, for example, according to your ranking, now your choice is between A2 from the algorithmic ranking or P1 from your own ranking, the top choice from your own ranking. And because these come from the same distribution, with some work, you can show that actually it's better to draw from the first position than the second. And so in fact, you would do better taking from your own private ranking. So basically, when your competitor is using the shared algorithm, and these are equally accurate, then you could be in one of two cases. In one, it doesn't matter what you do, and in the other, you do better with your private ranking. And therefore, because it's some weighted combination of those, you should use your private ranking. Okay, so that's now because this holds when they're equal by some strict margin. By continuity, it still holds even when phi sub p is pulled down a little bit. And so as a result, you actually get this gap that even with a slightly less accurate private ranking, you should still want to use it when you know you're moving second. And finally, we get to the game when you don't know which order you're moving. Right now, it's in a random order. You might move first and you might move second. But this fact from the previous slide is basically mainly what we need. So suppose we're moving in a random order. Imagine you know your competitor is using the algorithmic ranking. Then, as essentially we've just established, that when the two accuracies are equal, there's a higher payoff to use your own private ranking. If I start moving up the algorithmic accuracy, picture this as some spectrum of accuracy values. As I start pulling the algorithmic accuracy up, I will eventually get to a point where you should use it because it's just so accurate. Which means if I shouldn't use it here and I should use it here, we get to a point where I'm indifferent, some phi sub a star that's bigger, where it actually doesn't matter which one I do. Okay. What you can show using some of the arguments like on the previous slide is that at that moment, social welfare would be better if both firms use their private rankings. But because they're indifferent, it's a weak equilibrium for them to choose the algorithm. And if I pull that accuracy even slightly higher, it'll now be, in fact, strictly better for them to use the algorithm. But by continuity, it's still socially worse. Okay, so I find this point of indifference. It's socially worse for them to use the algorithm, but they're indifferent. and then I pull things slightly more to the right, I make the algorithm just slightly more accurate. Now it's strictly better for them to use it, so it'll become the only equilibrium. But by continuity, it's still socially worse. Okay, and that's essentially how the Brace paradox is coming into play. And it's essentially all coming from this fact that if you're moving second, then there's actually value in randomizing your behavior compared to the person moving ahead of you, as long as you can keep the accuracy comparable. Okay, and that essentially is then what turns into the dangers of monoculture with a fixed order. And then in this game, you end up with the Brace paradox because you actually have a bad equilibrium. Okay, so this is roughly what I wanted to say about monoculture. I want to dive into a second brief topic that gets into some of the issues in the actual construction of these rankings. So far we've said, right, making more accurate ranking available to everyone can actually cause surprises. There are a number of other directions. I've been talking about two firms. I've been talking about particularly simple models. But what I wanted to think about was, so far I've been treating the noise in the rankings as just a basic primitive. There just is noise. We've also been thinking about a little bit toward what is causing noise in rankings. And so I want to show some results as essentially at a lower level of abstraction that I think are also suggestive of some of the ways in which auditing of the algorithmic pipeline can produce some useful insights. So one basic way in which noise gets introduced into rankings is through the process of featurization of individuals, right? So essentially, the act of producing features is a simplification. And often we further simplify by only keeping some of those features. And all of these processes of simplification are introducing noise into the ranking. And a premise that I would like to argue is that using these simplified computational representations of individuals puts us in a situation that actually has strong parallels to some of the behavioral literature on models of stereotype formation in the way that humans engage in decision making. And so I want to talk about some recent work that Senthil Mullainathan and I have been doing, which we're continuing to pursue, showing that in fact simplified models incentivize decision makers to engage in bias, and that bias is directed toward groups that are already disadvantaged in the decision. Okay, so, and this is in a way sort of some of the ways in which the simplifications created by this machine learning pipeline can turn forms of disadvantage into bias, much in the way that stereotype formation can as well. So in order to do this, I'm going to briefly introduce a sort of extension of the model I've been talking about. Let's take away the notion of competition. Let's say there's a single firm, but let's kind of get into the internals of how it's arriving at its ranking, okay? So imagine, again, that we have applicants and that we're ranking them. Applicants, let's say, are described by Boolean variables, x1 up to some higher dimension xk. And there's, again, some value attached to each applicant. They're described by a productivity function, f of x, if you have features x. And this firm is planning to sort people by f value and then admitting the top r fraction of all the applicants, right? And we could think of this, as hiring. We think of this as, again, a metaphorical story about PhD admissions, where I'm looking at features and I'm saying I'm going to take the top r fraction of people who apply. Okay, now I want to argue that the process we're talking about is going to interact badly with notions of disadvantage. And so I should talk about the notion that there are two groups in my setting, an advantage group A and a disadvantage group D. So in a way, there's this feature vector, but there's also an extended feature vector, x comma A or x comma D, saying what group they're. Now, the function f is independent of the group membership. So f of x comma A is the same as f of x comma D, which is just f of x. It says this is a decision maker who actually, if you ask, would you like to know the value of their group, this person's group membership, they'd say, I don't care. I have everything I need to know in the set of features. In what sense then is there disadvantage? Well, there's disadvantage because the features themselves are distributed differently in the two groups. Namely, if x is a better feature vector than x prime for this purpose, right? If it confers higher values of the productivity that make you a stronger applicant, then it's more overrepresented in group A than a worse feature x prime. Okay, so in this sense, group A is advantaged in that better feature vectors tend to be more heavily distributed on them. Okay, and nonetheless, the decision maker is going to rank based on this. And so you could think of this decision maker as they're not biased, because from this second block of points here, they don't care what group someone comes from. But they're also sort of lazy in that they're not particularly concerned about the fact that there's disadvantage being manifested that's favoring group A in their decision. Okay, now let's look at how this ranking gets perturbed. Noise gets added to it as it passes through the process of simplification, okay, and featurization. So in order to do this, I'm going to show you an example that we can work through in the next 7-8 minutes in real time, and then I'll wrap up the talk. So it's simple enough that we can kind of do the calculations in our heads. Obviously, the sort of examples we have in mind are much more complicated. Let's imagine there are 2 Boolean variables in the world, x1 and x2. And the true criterion is just a conjunction, x1 and x2. And let's imagine that advantage is represented in the sense that applicants from group A have xi equal to 1 with probability 2/3. Applicants from group D have xi equal to 1 with probability only 1/3. Okay, right. So if this is PhD admissions, we could think of x1 as something about grades, and x2 is we evaluate whether this person did high quality research as an undergraduate, for example. Okay, and we rank by this, and we take the top R fraction. And if you do this, you'll see that at all small admission rates, in this case less than or equal to 5/18, let's imagine A and D are in equal proportions in the population, right? So the number from group A who have this configuration is 1/2 times 2/3 times 2/3. Then at all small admission rates, everyone who's admitted will have F value 1, the highest possible. And only a 1/5 fraction will come from group D. That's how the disadvantage is manifesting itself. Now let's talk about how simplification is going to warp the ranking. So a common thing that happens is that we only collect some of the features. In this case, for example, maybe we only collect x1. Why is that? Well, perhaps collecting x2 is too expensive. In our story here, it's easy to look at grades. It's hard to actually evaluate someone's undergrad research. That's a very costly operation. Perhaps we're simplifying in larger instances than this one for purposes of interpretability or cognitive complexity. We might be doing it because we're regularizing and we want better out-of-sample generalization. For all of these reasons, we might omit one of the variables. And in that way, we'd move from the 8-line truth table to the 2-line truth table, which just says all we know is the value of x1. And we're just collapsing all those rows into larger cells, and we're admitting somewhat indistinguishably from those cells. Right? So that's what we call an F approximator. We collapse rows, we assign each applicant their expected value conditional on what we know about them, and we admit in this order. Now at all small admission rates, the average F value went down. It's 5/9, not 1. The fraction from group D went up. It's 1/3, not 1/5. So relative to the true F, we have gains in equity, losses in efficiency, right? Larger representation of group D, less value of F, right? And that's what happens as the ranking becomes noisier in the presence of disadvantage, right? And so there is this trade-off, but there are also 2 difficulties going on that I want to summarize briefly. One's really a difficulty, one's maybe a missed opportunity. The difficulty is that if we were to ask the decision maker originally, would you like to know the value of group membership, right? You know x1, x2, would you like to know the value of group membership? They would say, no, I have everything I need in x1, x2. After we simplify, if we were to ask that same question, would you like to know the value of group membership, right? Having taken out x2, now the decision maker, who's an F maximizer, they just want to maximize F, right? They would say, why, actually, yes, I would now like to know the value of group membership. Because if I knew the group membership of this person, then I would create this expanded 4-line truth table where I used knowledge of x1 and knowledge of the group, right? And I would admit in this order. I'd admit first from group A, then from group D, because group A contains conditional information about the missing x2, right? Right, so this was not a decision maker who actually cared about group membership when they had all the information, but because they're trying to maximize F, now they do. In other words, what's happened? Simplification has transformed disadvantage into bias, right? It's converted one problem, disadvantage, into a second problem, bias. It's created a pernicious incentive to seek out group membership, right? An incentive because it makes you improve F, and pernicious because it's hurting group D. And what's interesting is that this is in a way very close to models for the formation of stereotypes by humans, right? It is often argued, both empirically and theoretically, that in situations of rapid decision-making or low information, we are particularly prone to fall back on stereotypes and in ways that often harm disadvantaged groups. And that's exactly what's happening here, right? What's interesting is that this idea that in the absence of information, we seek out knowledge from stereotypes, we think of that as potentially a very human thing. But it's arguing here that even an 8-line truth table will do this if you instruct it to care about the value of f, and then you withhold information from it. And then briefly, I want to talk about a second issue that comes up. Let's call this one a missed opportunity, which is that in a way, simplification isn't even the best trade-off we could make between efficiency and equity. Right, so let's recall our two-line truth table here, which lowered efficiency from 1 to 5/9, but raised the representation of group D from 1/5 to 1/3. Right? That move is actually not on the Pareto frontier of what can be done. It is not the optimal trade-off between them. Because what I could do is take this two-line truth table and strategically unsimplify it to this three-line truth table. And again, we'll admit from top to bottom. So we first look at anyone where x1 equals x2 equals 1, and where group membership equals D, right? Those people have an average F value of 1, and I just take them first. And then I take the rest of the top cell, which now has average value of half, and I admit that way. Right, so rather than pull indistinguishably from this top row, I break that top row into 2 rows, and I admit in this order. I've raised F, and I've raised D simultaneously. And in case we think of this as sort of an artifact of, sort of this model or this notion of truth tables, I would argue that this is actually, again, a sort of stylized parallel to discussions that we've had, and I'm sure you've had, and in a sense, anyone who runs admission thinks about, which is you have a discussion where you say, we would like to get greater representation from group D, but the problem is we just don't have enough information in our applicant pool to be able to do that. And then you say, what if we were to run a summer internship program after junior year of college, where we bring people from group D onto campus, they do research with us, and at great expense, we learn about the quality of their research. We now fill in the value of X2. And people who now do particularly well in that program, we flag them in our applicant pool the next fall. And in a way, we win both ways. We get very high quality applicants and we increase our representation of group D, right? And that too sort of emerges immediately from this model when we begin seeking Pareto improvements on our simplified rule, right? So I think it raises the interesting question when we have a decision rule. The fact that we have, lowered efficiency, gained equity, does not mean we're on the Pareto frontier. And in fact, in some sense, we actually likely aren't. And so there's an interesting question around the idea of, sort of finding optimal unsimplifications of your rule to try getting these Pareto improvements. So that's the picture at the low level, at the feature level of how these rankings get warped, right? Simplification creates noisy rankings. And in one direction, it leads to incentivized bias as we seek out this variable. In the other direction, it leads toward potentials for Pareto improvement, where we can simultaneously improve efficiency and equity. And essentially, the theorem that Sendel and I were able to prove is that what happens in this example happens in general. That essentially for every Boolean function f with real valued output satisfying this disadvantage condition, as well as a kind of genericity assumption that I won't go into, and for every simplification of it, then these two things hold. One, there's in fact always a way to unsimplify it. There's always a way to strictly improve it in both efficiency and equity. And second, if it didn't use group membership, then adding group membership as a variable increases efficiency and reduces equity. In the sense, it creates a pernicious incentive to turn disadvantage into bias. Okay, and so with that, I'll stop here. The first technical piece of this talk has really been about noisy rankings as an issue in themselves and the ways in which monocultural convergence on algorithm can lead to some surprising losses of efficiency. And the second part has been tried to open up the notion of where these rankings come from, to think about the simplifications that we inevitably make in formulating prediction problems, and then to show some of the issues that come up there, both the risks of incentivized bias and the opportunities for improvement. And I think more broadly, all of this is part of a broader discussion about the way algorithms do make decisions in fundamentally different ways. And in that process, they allow a new level of really concrete, explicit discussion about the decisions we make and the way biases and other difficulties can enter the process. And I think what's interesting is how many fields really can potentially play a role in setting the priorities for this area going forward. And I think that's going to be a very interesting opportunity for computing to engage with all these disciplines in that conversation going forward. Thanks very much.
Yeah, there's a question from Matt Kleinberg.
Yeah, I see that. Okay, so I think all of you see the question, but so for the competing firms model, yeah, what's an intervention that would address this? So it's an interesting question that we've been that we've been trying to think about. I mean, obviously, you know, I think one direction we've been thinking is that in the same way that the computer security literature, after first observing the risks of, you know, systems level monoculture, began making an argument for artificial heteroculture. I think, you know, one argument that would sort of take us a bit outside the model would be to say, if I'm able to produce one algorithm that, you know, achieves this level of accuracy, could I potentially produce, you know, several random variations on this, right? So potentially the optimization landscape for my algorithm is relatively flat near the top, and there could be potentially variation in it that's sort of neutral with respect to performance. But I think it's an argument that neutral variation in the predictive models that we use, you know, even if it's not performance enhancing, as long as it's not performance decreasing, it could potentially confer other values, such as separating the predictions that we make and potentially avoiding these problems. But I think, yeah, the suggestions that you're making here, like hybridizing the algorithm in private rankings, learning the order and so forth, I think all of those are interesting questions as well. But I think, yeah, our thinking has been sort of toward the idea that we often see situations where there's a lot of opportunity for sort of neutral variation among the optima, and sort of thinking that could actually produce sort of benefits given the risk of these praise paradox phenomena.
I have a question to Jon. So maybe towards the end you quickly hinted at this, but sometimes economics type models are describing a possible bad thing that can happen, and it would be nice to know if there's a prescription. Like, so it feels kind of like, you know, prescribing something for general networks using GNP or some simplified model. So
Yeah.
what's your thoughts on those?
Yeah. So I mean, again, I think in the first part, it's sort of, you know, I think it was novel to us. So to sort of take the two pieces, like at the level of the monoculture, I think it was novel to us the idea that this is a sort of a new distinct risk from monoculture. I mean, we've been thinking of it as, you know, sort of global random shocks to the system that are sort of catastrophic. This is a different, more low-grade systemic problem that, again, I think, you know, argues that there's value in creating heterogeneity in the models that we're building. So I think a general, you know, recommendation of sort of, you know, kind of making sure to preserve the heterogeneity in model development could potentially have value, you know, and this is obviously an extremely stylized model that's making that suggestion, but it's potentially a more qualitative recommendation that emerges. In this second part, again, I think the thing we found striking was the way in which this suggests both the premise and also even potential recipes for looking for strategic unsimplifications of our rules, right? So when we're operating in the presence of disadvantage, as we almost always are, to think about ways in which we might not be on the Pareto frontier of efficiency and equity, and looking for interventions, right? Because we're often simplifying because the complex rule is costly, but that means we're often operating within some kind of a margin of budget. And the question is, can we use our budget more strategically to fill in certain cells of the prediction function in ways that might create Pareto improvements?
So in particular, did you get some new insights about how to run that admission process?
You know, I mean, again, I think it's, you know, it's, in a way, it's sort of, I think, a kind of sharpening of insights that we had in a qualitative sense, which really was this idea that, you know, focusing your information gathering efforts non-uniformly is, you know, I think, and that, I think in general, that's been one idea which has emerged, I think, from a lot of these places where humans making decisions with quantitative tools. One thing that the quantitative tool can potentially help with, even when it's not a proxy for your actual final decision, is as a kind of guide toward directing your efforts, right? So it's often the case that you end up looking at a huge number of instances as a human decision maker. And, you know, if you allocate your time equally across all the instances, that is almost surely not the correct allocation of effort. It's much more likely that the correct allocation of effort is to find places where added energy and information gathering is going to cause correspondingly high gains. In a sense, the model's deriving a lot of its power from that. And I think that's sort of a more high level takeaway also as well, that the quantitative tool, even if we don't trust it to make decisions, we may want it helping us figure out where we should be spending our energies.
And Mark has a question in the chat. Should I read it? Is the mechanism
Sure, yeah.
behind monoculture risk related to winner's curse? That the hidden variable
related to winner's curse
is whether the applicant already shopped the other phone.
Yeah, I guess you could. It's an interesting point. I mean, I guess at some level, yes. Right. Obviously, I think of them as Yeah, it's a very interesting question. I think of them obviously as distinct just because of the syntactically distinct trappings for them. But obviously, what's happening is that because I have a competitor who makes a choice, I now have conditional information about my own choice when they're correlated. So in that sense, yeah, there's clearly an analogy. It's a very good point. Whether there's some mileage in that analogy, given that the settings are quite different, it's a very interesting question.
So I don't see any other questions. We'll thank Jon at this point. And anybody who wants to chat with him can ask to be promoted to panelist. Emily is still here. She can do it. Let us know. Thanks very much, Jon.
Thanks very much.